Hi, my name is Weston Fuhr, and this is my final project video for ENME435. To provide some background on this project, the main goal is to generate a high-quality point cloud of a target of interest which we selected at the beginning of the semester. To generate the point cloud, throughout the semester we also created our very own LiDAR scanner, which will be shown later. With my target being Testudo, obviously the key features are the legs, the torso, his arms, and then also the head, as well as other details such as the shell and the arms. So there are plenty of creases and features for the LiDAR sensor to try and detect. The main reason why I wanted to scan Testudo was simply because it is our school mascot, and I thought it would be interesting. Before getting into the LiDAR device that I designed, it's important to go over the basics. As you can see in the image, the way the LiDAR sensor we built in this class works is you have a light source on one side and a receiver on the other. In this case, our light source is a line laser and our receiver is a camera, and they're offset by a set distance, and then using this offset, we can use trigonometry to calculate the range to our target object. This is my walkthrough of the LiDAR mount that I assembled. You can see the key components are the Raspberry Pi with the Raspberry Pi camera, the Arduino, which acts as a power supply for the line laser, the power brick that will power both these devices, and then of course the chassis and tripod mount. In terms of how it functions, the laser acts as the emitter, and then the camera is the receiver, which will look at the laser line. And then since we know the distance between the laser and the camera, we can then interpret the image that the camera is seeing and determine the distance to the target. During the alignment process, the laser itself is not entirely straight. However, looking at the camera feed, we can see that the laser line is mostly straight. It just has a bow to it from the top and bottom. And what I realized is if I move this ever so slightly, it adjusts the straightness shown here. So when I'm doing the actual measuring, I'll have to make sure that my mount is set up in such a way that it's facing not entirely straight. And the other thing I noticed is I think it has to do with my camera module here, where you can see that it's not sitting perfectly in line with the frame itself, so it's actually tilted this way. So I think when it's crooked like this, the camera is looking straight, but everything else is tilting, so this will be something I'll have to account for. When calibrating my LiDAR setup, I ensured that the laser and camera were fixed in their position, and then I began to take the calibration images in the 6-inch intervals away from the wall. I started at 36 inches as I found this was the minimum distance that I could get a reading from. And in order to ensure the accuracy, I hung a string from my sensor so that I could precisely determine the distance from the wall. After collecting all of the calibration images, I selected one to put into the color picker program to determine the optimal threshold, and then I ran it through the calibration code, which plotted the distance points against the theoretical point, and after changing just one of the scaling parameters, you can see that the theoretical calibration curve matched up nearly perfectly with my own collected data, which is the red dots. With calibration complete, I was now ready to scan Testudo. So as you can see, I have my scanner set up on a tripod. The horizontal movement locked, so it can only move up and down. I have my laser going, the Pi being powered by, or both being powered by the power bank, and then on my laptop, the virtual desktop running, with the program and the process I've been going with. So right now I've been taking the angle by placing my phone at the top horizontal edge or top edge here so I can get the angle. I enter it into the program and then it takes the picture. So I've run the program. It prompts me to enter the angle. Right now it's at 300 degrees. I enter 300 degree angle. It will now take the image. You could see the laser there on Testudo's legs. When it is done, the image is now loaded into my Testudo images folder, which I will then upload onto my laptop when I'm done. This is the setup for night 2. Today I'm scanning the, right side of Testudo. Here is a time lapse of scanning Testudo. You can see that I move the laser up by 1 degree at a time. The only issue with the location of this target is the road nearby, because I'd have to wait for cars to go by before taking an image. One of the challenges to this Testudo is where it's positioned, because you have easy access to the front and sides. However, the back, given that it's up on the wall, is somewhat hard to access. So I've positioned my tripod up on the ledge here, and I'm not getting the full base, but I'm able to now scan the backside of Testudo with my scanner being placed back this way, facing out, and this will complete my point cloud of Testudo. With the image data collected and transferred onto my laptop, the Testudo back folder, which contained all of my back images as an example, when I run the data generation code, you can see it loops through every single image, applying the threshold values that I selected using the color picker. And then after this has run, it generates the text file, which I load into Cloud Compare to generate the point cloud. I input the raw text files into point cloud and began to trim away the noise. Here I am starting with the back side of Testudo. Now I'm moving on to doing the right side of Testudo. Finally, here is the left side of Testudo being trimmed. With all the sides trimmed, I put them all into one Cloud Compare file and began to manipulate the sides to create a 3-sided Testudo. Now I added in the point cloud for the back of Testudo to complete the point cloud. Here is a final 360 of the full Testudo point cloud. Overall, I'm very happy with the results. All of the main features and characteristics I identified earlier can be identified on the point cloud. Here is the same 360 with the point size significantly increased. As stated before, I'm very happy with the results, and I believe this Testudo would be easily recognizable and easily identified by most individuals. In order to create or attempt to create a mesh of Testudo, I started by importing the combined text file that contains all the points required to create the complete Testudo. And then I followed the steps provided to assign the normals, and then use the Poisson Recon plugin to generate the first mesh. As you can see, the mesh did not turn out the greatest, but overall I'm very pleased with how dense and high quality the point cloud was. Thanks for watching.